Gentlemen, ladies I don't see, dear visitors of the fair, I would like today talk about what is already mentioned, how to come from a diagnosis technology in sensor technology to metrological confirmation, or in other words, I like to present a methodology, how to reduce the calibration cycles, how to make smaller calibration cycles. And I will concentrate a little on sensor technology for the process automation. And I think I start with a picture of the Ludwigshafen Chemical Park from BASF. And I like to ask you, what do you think, how many real process sensors are installed in this factory, in this plant? With process sensors, I mean not small sensors like temperature sensors, but real sensors, spectrometers, flow sensors, level sensors, pressure sensors. What do you think, how many are installed here? I think you get something from him when you have the right answer. How many? 10,000, one number? Do you know? How many? Something in between, it's about 400,000. This is not a problem, but the challenge is these 400,000 sensors have to be maintained. They have to be checked. They have to calibrate it. And everything which helps to limit the number of calibration will be very welcome. And there we'll talk about. But first I will talk about a little about the need for digitization in the process industry. And I start with a paper which was published about 2 years ago, quite recently. There were all members of the chemical companies in Germany and also the manufacturer of sensors in Germany came together and thought about what will be the future for the sensors for the next 10 years. And as one result, they mentioned that for use in safety and other applications, a high degree of condition monitoring and self-diagnosis is required. That means what the user of such factories need, they need sensors which do self-diagnostic and which for this same purpose don't like to get calibrated so often. And I will talk about how this will be achieved. And one of the goals, one of the technologies, the new technologies which helps to make this digitization successful is the so-called NOAA system. NOAA system means that, maybe I have to start with, the standard sensor today in process automation, process plants, is just connected to the control system just by 4 to 20 milliampere system. That means this is just a system which is 50 years old and still in use, still prominent in use, but is not able to transport more information. And by the second channel, the so-called NOAA architecture, you are able to also give more information from the sensor, more information to the sensor. And this is some of the prerequisite to do what I just will talk about. No? Okay, I don't want to take it too much. I come to my agenda. What is, in general, a process engineering process, or in Germany, ein Prozess? Then I will talk about diagnosis, and this, what is required, a so-called IoT ecosystem. And then I will come to the main question, what can I do to reduce the number of calibration for process sensors? That I not do I have to calibrate them once a year or once in 2 months? But maybe then I will have to calibrate it once in 5 years. And this is what I'm going to tell you. But let's start with the other things. First, I want to explain or to lay out what is a process. A process is a set of interacting operation in systems through which matter, energy, or information is transformed or stored. That means when you build cars, that is not a process in the sense. This is a manufacturing process. But we are talking here at processes which takes place in chemical industry, which takes place in pharmaceutical industry, which takes place in food industry. For example, in pharmaceutical industry, you need sugar and made insulin out of sugar. by help of bacteria. When you go to chemistry, you may have a raw oil and make benzene out of it. When you go into the food industry, you have milk and make cheese out of it. And these are all processes. And the general picture is that you have raw material which is somehow processed and get out the result what you want to have. Cheese or insulin or benzene. And gasoline, not benzene, gasoline, sorry. Ne? And in order to control these processes, you need sensors. And this is the purpose of these 400,000 sensors which you have seen in the BASF plant. And these are typical examples for process sensors. These are from the company I used to work with. This is a flow sensor, a level sensor, and this is a pressure sensor. And they cost about €1,000 up to €10,000. Quite expensive, these type of sensors. So you need there's also a lot of money installed in such a factory. No? The typical way a sensor works internally, such simple. You have some way of activation. You have some type of sensoring. They are processed and they get the measurement data out of it. And the typical measurement data today in process automation is that they use a 4 to 20 milliamp or current loop to give the information to the system. In the future, or today, which is going to get more and more, you will also have a diagnostic system internally built in the system. That the system internally checks whether it's working or whether it's not working. And this is another output. This is not the same output as this one. And this needs another digital environment to process these. Okay. And this is the right environment. You have the standard automation pyramid, where you have the normal connection like this, and there's parallel to that this other here, maybe it's a cloud system where you process the diagnostic data. Just to mention it. This name's IoT architecture. This is an example that there's an IoT architecture where a lot of services are available to deal with this data. Just briefly. Okay, let's go back. This is an example. Maybe with this IoT system you have one feature where you get an overview of all the status of your devices. Maybe this example, you have 476 devices which are okay, 3 which are not okay, 3 which need maintenance, and so forth. But this is only possible with this IoT ecosystem. Okay, and this is, you can also dive deeper in order to get more information about that. So, the first stop over now. Not for you, but for me. No? So, to explain what I have told, the second channel in process sensor is a suitable architecture, is the basis for the use of extensive diagnostic capabilities. This is the digitization requirements to do this, what I'm talking about. This can be used to provide function for error detection, also predictive, and thus confirmation of proper operation. And when you ask a plant operator and tell him what you want first, and he said, my first wish is no calibration, but my second wish is that errors are told me before they occur. And this is one way to get this, to get to this wish list. Okay. Okay, the process industry can use this function efficiently. So, and now, we have talked about diagnosis. And diagnosis only is able to say the device, the measurement device, is going to fail, is going to get out of operation. But now let's talk about metrological property. You may have the case that your device is it's still working, but it's not metrologically okay. Maybe you have a difference in output, or the measurement uncertainty is not okay anymore. No? And this are now talking about how can metrological properties be tested beyond pure diagnosis, or how can I extend the diagnosis to also measure metrological properties? And one question, which a detailed question, is how can metrological properties be tested beyond pure diagnosis? And one answer is of course, with regular external calibration and adjustment if necessary. This we do all the time, by just calibrate it every 2 months, every 2 years, what is necessary. This may require interruption of the process. Consider you have a chemical plant with a tower of 50-meter height, and your sensor is put on top of this tower. How you calibrate it? You can bring, you have to pull out the sensor to bring it to the calibration stand, or you might also think to bring the calibration stand to the device. But then I show you something. You have to remove the sensor, maybe necessary. There's also a calibration infrastructure required. And this is a calibration infrastructure for calibrated flow devices, flow measurement devices. This is about 10 tons, has a height of 20 meters, and costs 2 million. And this you cannot put to the device. You have to put the device to this calibration stand, to the calibration infrastructure. So the result is calibration is expensive, calibration is cumbersome, and calibration is hard. And the result is, and the wish is, do calibration as rarely as possible, at best avoid it. The answer to that is the best solution would be self-calibration, that the sensor is able to make the calibration itself. Here we have an example for that. For a temperature sensor, we have here the standard temperature element, the PT100, and then you have a ceramic put on it, and this ceramic has the property that it changes its crystal structure exactly at a certain temperature. And this you can use as an internal fixed point, and then you have your calibration yourself. When the temperature reaches this fixed point, you have a reference internally and say, okay, is my measurement already okay, or do I have adjusted? This is already available as my former company. It is very successful. But from where you get internal references for pressure, for fill level, for flow, for pH. When you have this, it would be no problem. And so I propose an intermediate way to approach the goal, how we can reduce the number of calibration, or even how we can avoid the number of calibration. And this is the third answer. Also, the second, sorry, sorry that I forgot it. Sorry very much. How can metrological properties be tested beyond pure diagnostic in the future using traceable internal reference standard, what they call NIST on a chip? And I think you will have also a presentation this afternoon to explain it in detail. And the NIST, this famous institute from the United States, they already are in preparing or just presenting or just have prototype of all these properties which you can reference within the device. You can have small chips which you put in your device and have a reference for a time. You have a reference for a magnetic flux. And that means you can do, when it's successful, when it's done, I don't know how long it will take, some weeks, some tens of weeks, I don't know, some years, some tens of years, I don't know. You will be able to completely avoid any calibration, external calibration. This will be done totally in time, in the device. But, and here as you see, I like this example from the website of NIST. This is a coffee bean, and this is an atomic clock. And this atomic clock you can easily put in your device. You don't have too much space for that. However, I don't know what does it cost? No? Okay. So, and now comes my idea or our idea. When you have a measurement device, you have a certain component. You have maybe a primary sensor, then you have a clock, then you have an amplifier, then you have a voltage, and at the end you get the result. And my idea is, our idea is, not to test the entire system, but maybe some components which are accessible, you measure and check against references. Not 100%, but a few of them. And this I have written here, components, not all, but many, that contribute to metrological quality must be tested against internal references. And this I name metrological testing. And voltages you can check, frequencies you can check, amplification you can check, but also mechanical parameters. You try to find out what is the degradation of your device, which needs regular calibration and adjustment. And then you say, okay, what of these components I check in order to reduce the probability that calibration is necessary. I have a few examples just to show you. When you want to check a clock, you need a second clock. And when the clocks are different, to say there's something out of order. No? Second is when you have, for example, these flow sensors, they measure a phase shift. And you create a phase shift virtually and then check whether the electronic is still working the same. You have also internal reference. Second example is you have an amplifier and you just measure back what is coming out and by you check it. And that means all quantitatively contributing to calibration behavior, calibration performance, you check explicitly. But this is important, not all components, but the components which are accessible for that. This is already available in products from the company, from many companies, but also from the companies Anderson Hauser, and their name is Heartbeat, and they even are able to produce a verification report, a certificate, which are put out of the device via this digital interface, which I just described before. That means you can say you get this calibration, this certificate. It's not a calibration certificate, it's a certificate that a verification of the important components is okay. And now I want to show you how this leads to a longer calibration period. And the idea is, again, a stop over to keep in mind what I had talked so far. By comparing with internal references, metrological properties can also be checked as part of the self-diagnostic. But not all components of a process sensor are accessible for this inspection, not all. Such a check can be documented via an IoT system, as I just showed, and implementations for this type of checking, for this type of metrological checking or metrological verification are already available on the market. And here are just the comparison of the three methods. In general, you have the metrological testing, what I talk about, the self-calibration, and the future method of, I name it just NIST on a chip. This is a future solution. This is an ideal solution, but this ideal solution is not available for all measurement devices, for all measurement methods. This is available for all measurement methods. The costs are good. It's a few electronics which you put, for example. Cost here maybe medium. I don't know what this, I think medium to bad. No? But at the time today, you might have that, which is only available for a few measurement types, or this, which may be available for a lot of measurement methods. And now I try to tell you how this will lead to a change in calibration period or calibration time. Okay. During and why do you calibrate? After you have made a calibration, yeah, how big or how large is the probability that the device fails just after you have calibrated it? 0, because you have calibrated it. But with time, the probability of error increases. You say, okay, after 1 week it's still okay. After 3 months, maybe also not okay. After 6 months, I check it better because the probability is high that the calibration is out of calibration, that the calibration is out of setting. And for this purpose, you do a calibration. And you do a calibration here, do a calibration here, do a calibration here, and always put the probability that it starts again to 0. And this is a normal way. Half a year, maybe half a year, half a year, half a year, half a year, over the lifetime of the device. And this is the calibration interval which you have. And you should know calibration intervals when I see with process sensors. For a pH sensors, you may be 1 week, 1 month. For a pressure sensors, 1 year. For flow sensors, 2 years. It depends on the sensor type. Huh? But even if you have to calibrate every year, it's difficult for these companies. It costs money, as I explained to you. And now let's look for the metrological verification, how it looks in. Then I have also internally calibrated or internally verified. I just started and check, is the time in order, is the amplification in order, is the voltage in order, is the phase in order. And with this in order, I say, okay, I can start again. But because I don't not cover all devices, all components, there is still the probability is not going to 0. And in order to put it back to 0, I make again a calibration, but much less often, much more seldom. And then you have a new calibration interval, which maybe, I don't know, 3 times, 4 times, 10 times the calibration interval which we had before. When you, on the other hand, have self-calibration, it's easy. It works internally, tuck, tuck, tuck. You can do it every day, and it works forever without calibration. But as I mentioned, self-calibration is not available for all measurement methodology, for all the measurement methods. And this is almost what I want to tell you. I think I have something to summarize. First of all, the second channel. The standard channel is just to communicate the measurement data, and the second channel in the process industry is necessary to also support diagnostic information. And this is done by an I2 ecosystem, and the German chemical industry, I think the world chemical industry, is heavily working on to get away from this, to get to this new system. No? So the self-diagnostic functions which are now available can be extended by means of internal reference to check metrological properties, not only function, but also metrological properties. And this can reduce, not eliminate, reduce the explicit calibration, the need for explicit calibration. Do I have another? And self-calibration for process sensors would be ideal, but it's not available. And maybe in the future, we might have with NIST on a chip the probability to do full self-calibration, but this is still in the future. I don't know whether I will survive it. No? Okay. Last, never believe it, check it, and thank you for your attention.
Yeah. Dear Karl, thanks a lot for your very fantastic talk, and I'm sure you will survive. I'm very sure.
Really?
Because yes, I think our colleagues from NIST, they are working in a very good way on it, so you have a good chance. And I would like to see it also in my life. So.
Oh, very good.
Yeah,
so I'm looking forward.
So,
I bet for you.
Are there any questions from the auditorium?
That's the case. Okay, thank you.
So,
So you talked about the 400,000 sensors that are in that Bosch factory, and I'm just curious, of all those sensors, is there one particular unit that is sort of the most problematic?
Yeah, they have 2 types of sensors, or 2 types of sensor application. One application is process control, and the other is safety. Safety against explosion proof. They will measure the absence or the existence of certain gases, And with these sensors failed, you have a real problem, and they are very critical. And normally they have a map. They say this sensor has this critically, this sensor this critically. And from this, they define the number of calibration you have to do. Maybe when it's very critical, they calibrate it, I don't know, every 3 months. When it's not so critical, maybe it's just water supply, they calibrate it every 3 years. So they're very important. They think very much in critically dimensions.
Okay, thanks for the question. Are there other questions?
Not the case.
So thanks a lot once more, Ulrich. We now make a coffee break.